If you don't have Haskell installed, it's helpful to actually have it because there are examples we're going to be running through together. The package is named GHC. You can install it through Brew or just your Linux package manager. Okay, so to get started, we're going to talk about what Haskell actually is. So Haskell is a functional, pure programming language. So most of you know C++ from just regular classes, and C++ is what's called an imperative language. An imperative language just means that when you give it code, the code is running in a sequence of steps from like top to bottom. So you run one line of code, setting a variable, running another line of code, adding something together. That's what step by step. Functional language don't have that sense of step by step execution. What you do instead is you define some kind of function, and then by chaining functions together through recursion and composition, just calling multiple functions, you can compute things. So there's no step by step sequence. That's what it means to be a functional language. Haskell is also a pure functional language, so not all functional languages are pure. So that's one good thing about Haskell. Like if you look at Lisp, for example, Lisp is another common functional language, but it's not pure. And pure just means that if you call a function multiple times, that function will always give you back the same value because there's nothing else that can affect the value of the function. Whereas in like C++, there's a joke where they say that in C++, if your code compiles, it doesn't mean that it actually works. But if it type checks in Haskell, that means it probably works. Because whenever you run a function, it'll give you back the same value. It's not going to change. The other thing is it's interpreted or compiled depending on how you're running it. So that's one really nice thing. If you want to just play around with the language, you can type GHCI in your terminal, and then you can type in Haskell commands, or you can get a file, put it in a file, and compile the file to like native machine binaries. So that means you can have the speed of compiled languages with the speed of development and iteration with interpreted languages. It's also statically typed. So statically typed just means that if you can't do things like assigning like an int to a string or adding an int to a string or just weird things with types. So in dynamically typed languages, you can do if there's an error in your types, then it'll tell you when you get to that error, which is kind of annoying. But in Haskell, if there's an error in your types, if you're doing something weird, it'll tell you before you even run the program, which is really nice. So another example, C++ is statically typed, Java is statically typed, but Python is dynamically typed. The cool thing is lazy evaluation. This is really unique to Haskell. I don't know off the top of my head many languages do lazy evaluation. And it just means that you don't need to actually compute stuff until like the user asks for that data back. Which means you can have some really complex functions, and normally it would suck because you have to call the entire function and get back only certain parts of the data you want back. But with Haskell, you can call the function and it'll only give you back what you need. So it ends up being very efficient. And the last thing here, so Haskell is very rooted in mathematical concepts, and that's really nice because when the Haskell developers want to add features or when you're writing code, things are very structured, and you can add features just because the language is already designed so well. And you don't have to know exactly what these things mean, but higher kind of types, algebraic data types, these are things that are Haskell has, and now other languages like Rust and Scala are taking because they're so nice in the language. So you don't know what they mean, but just know that if somebody asks you why is Haskell so great, this is one of the reasons why. Alright, so let's get started with actual Haskell code. So a convention throughout the talk is if you see those 3 greater than signs at the beginning, that means you're typing the GHCI prompt. So if I open up a terminal here, and I just type GHCI, then any command you see with the 3 greater signs I want to type in here. So for example, the first thing we're defining here is a variable a, and we're setting it equal to 1. So what we did there, we created a variable, and the variable is an integer. And then you can also define floats if you have a decimal point. You can define characters if you have single quotes, just like C++. And you can define strings, just like in C++ with double quotes. The weird thing here, though, is that only in GHCI you need the let in front of there. So we're going to get to running Haskell code in files soon, but you don't need the let in Haskell files, only for GHCI. If you're defining anything, you need the let. So go ahead and try typing those in into GHCI. But one thing you're going to notice with those variable definitions is that you didn't see any types there, but I told you that it was statically typed. And so C++ is statically typed. You also have to define your types, like int, for example. But you don't actually have to do it in Haskell. And the question is, why is that? Well, if you're familiar with the auto keyword in C++, that's something called type inference. And Haskell has type inference, but it's much more powerful than C++. In Haskell, there's something called Hindley-Miller type inference, and it's defined by these 6 equations. You don't have to know, but it is some very complicated math. Actually, this isn't that bad. This is very complicated math that kind of defines the integer or the variable as the most general type for the variable. And it's much more powerful than C++ in other languages. And you'll see that in a little bit. In the next slide, I'll talk about that, but the gist of it is that you don't have to define your types, but often it's good to do so if you want to be clear about your code. All right, so if you do want to define your types, if you want to bypass the type inference, you can use the double colon, which is the typo operator. It sets the type of whatever variable we're talking about. So note that here, this is in a file because I'm not using the 3 greater than signs. So I have a file over here. So this is the exact same code right there. And this is in a file. And if I want to run this code, I'm going to open up GHCI, and I'm going to put the :L command, and then I'm going to type the name of the file. So you can type at least one of those variables into a file. And then you can load this with this command into GHCI, and that runs the code, and now all those variables I've put in there are now available here. So that's how you define the actual type of the variable. Now, the question is, if you want to do this on GHCI, how do you do it? You can just add the type right after the definition. Over there, we put it on top, and here I just put it right after. So now, the :T is something you really need to know when you start off using Haskell. It tells you the type of whatever you defined. And because often Haskell is inferring the types for us, we often need to check what the types are. So if you define a variable A in your code, try running :T and then A and see what you get. So this is kind of weird because 1 is an integer, so we expect A to be an integer. So what I mentioned before is that Haskell not only finds a type for your variable, it finds the most general type. And this is called a type class. We're not going to talk about type classes today, but this is the most general type. But let's say I want a really specific type. I can do what I showed in the previous slide and define it specifically as an integer. And then when I get the type, oops, that was stupid. Then I get an actual integer. So you should know that :T, you can run it on all these things, and it'll make sense, but the weird thing is when you get to string over here, you see that it doesn't say string, it says char surrounded by brackets, and the brackets just means list, and we'll get to lists. And this is just saying that a string is just a list of characters, that's it. And just like in C++, C strings are just lists of characters. And this is, if you know C++, it's exactly a type def. There's no difference between these two types. It's just an alias for the type. Okay, so now, like I mentioned before, Haskell, you don't have iteration, and you don't have a step-by-step sequence of events happening. So what you do have is you have functions and you have lists, and you do all your combination to these two things. So let's start talking about lists. And the way you define a list is with the square brackets, and then all your values are separated by commas. So we can define a new list, let A equal 1, 2, 3. And then we can run some operations in the list. These are a couple of the useful ones we'll be using throughout the rest of the talk. So head of A gives you just the first element of the list. Tail of A gives you the rest of the list, except for the first element. And you can see why this would be useful, because if you think of recursion, recursion is usually operating on one element, usually the first element, and then recursing the rest of the list. So we need to have a way of pulling off the first one and pulling off the rest of it. So that's why we have these two functions. Then you have length, and then you have reverse, very standard functions. Note that when we call a function in other languages, often you surround the arguments with parentheses. In Haskell, it's just a space. So I just keep adding spaces between my arguments. Let me just show you this. So you know how it works. There are a couple more operations. Take is a function that takes the number of arguments you want to take off of your list. And this we'll talk about when we use infinite lists. It's very useful for that. So A is size 3, but if you take 2, you just take the first 2 elements of that. The next command up here is the actual indexing operation. This is really weird in Haskell. Normally you have A and then square brackets and 0 for the first element. And here you have 2 exclamation points to actually index your value. So this is going to give you the second value in your list. And then the last thing we have here is list concatenation. So in other languages, often you can just do like string 1 plus string 2 and get a larger string concatenated. Yeah? You have a question? Oh.
When I do the A bang bang 2, I get 3.
Oh yeah. So I did this all from like memory, so it's actually 0 index.
Okay.
Yeah. Sorry. So yeah, that should be 3 up there. So this concatenation operator, instead of doing like A plus B, you do A plus plus B. It's just a different way of writing it for concatenation. And this last one here is very important, but a little bit confusing. So if you know other functional languages, you've heard of the cons operator. It's just short for constructor. And all it's doing is it's constructing a list. So what we have is a single value and a list, and we put them together to construct a new list. We're not taking two lists, we're taking a value in a list. So there's a difference between the first one and the next one. So let me just show you real quick. So let's define a new list. B is equal to 4, 5, 6. And if we do A plus plus B, then we have a concatenation. But we can't do something like this. Because the first value needs to be an actual element and the last part needs to be a list. We can do something like that. What that does is it constructs a new list from the list B and puts 1 in front of it. So that's very useful. And you can chain this together with things like this. Right? So it's just it's like another function you can call. Oh, and then if you want to define like a single element, you can also do something like that. So it's just the exact same thing, but we're adding on to an empty list right there. Okay, so those are list basics. So because lists are so useful, we also define ranges over them, because we don't want to type every single element out if we're just having a range of elements. So the very first example here, just making a range from 1 to 10. So the list is going from 1 to 10. But what if we don't want to go by ones? Well, you can also do any other interval. So the second example is starting at 2, and then you type 4, and then you say the last element is 10. And Haskell figures out, based on the interval between 2 and 4, you're going to be skipping by 2s every time. So you can do intervals like that. Just note that it's not any more powerful than this. You can't do like 2, 4, 8 and expect to have like powers of 2 come out. You can only do something like arithmetic series. The next example is talking about infinite lists. So infinite lists are really cool, and they come about because Haskell is lazy. If you had an infinite list in any other language, you would have to evaluate the entire list, and you can't evaluate an infinite number of elements. But in Haskell, you don't have to evaluate every single element. So there's a function called cycle. And if I just type cycle 1, 2, 3, what it does is it makes an infinite list where it continues giving you 1, 2, 3, then back to 1, 2, 3, and so on. So it's going to keep giving me those values. But right now I'm asking GTI to print it, so it's evaluating all these values. So what if I only want to take 10 of those values? So I can do take 10, cycle 1, 2, 3, and then it gives me 10 values of the infinite list that I've created. So notice this isn't going forever because I only need 10 values. GTIs or Haskell is smart to figure that out. Another thing I want to mention real quick is that people often start off using Haskell and like get annoyed with all the parentheses you have to write. Because the function, the way it works is if I wrote this function, the way it would work is you would apply this function first, like from the right-hand side, and you'd apply this to that, and applying that to that makes no sense. So it would look really weird. But there is a way to do that once you're better at Haskell, is you can do something like that and put a $sign, and just like if that confuses you, you can use the parentheses, but just know that Haskell isn't one of those languages where all you see is parentheses. There's really clean ways to write things. So that was cycle. Repeat is obvious. It just makes an infinite list of whatever element you give it. This syntax right here is like a range without an end. So I said 1 dot dot and no end, and it gives you an infinite list of like incrementing numbers. So you have 1 to 10. And this last one is really cool. This last one is, we're defining A in terms of itself. We're defining A as 1, concatenated onto some other list, which is itself A. And if you run that, like, it's not going to be an error, it's not going to be an infinite loop, but because it's lazy, it knows that when you need 10 elements, it can make 10 elements for you. So this is something you can only do because Haskell is lazy. It's a really cool way to define an infinite list. Okay, so now we know how to define lists, so how to actually do stuff with them. So you can actually run kind of code inside of lists, which is really cool. And if you know list comprehensions in Python, Python got that from Haskell. So let me just start defining it in the GCI interpreter. So you have two things you need to see. First, you have your list, so you need the brackets. Then you have what you're going to return on your list, and then you're going to have how you get those elements. So let me just define something here real quick. What this is saying is, I'm going to loop through a list, and I'm going to return every element x from that list, where I define x as some other list. So if you look at this one more time, we're defining x as every element from 1 to 10, and then what are we doing it? The left-hand side of the pipe right there says we're just returning x. What if we want to double every element here? We can do any math operation on these elements. So if you go back to this example, that's all this is doing. You're defining x as every element from 1 to 10, and for each one of those elements, you're doing 2 times that as the first example. And if you're familiar with Python list comprehensions, it's very similar to that, except for you're not using like keywords like for. The second example here says that, let's say I want to define x as the number between 1 to 20, but I don't want all of them. I want to skip a few. And which ones do I want to skip? Well, I only want to take the ones where x mod 2 is equal to 0, or where x is even. Don't worry about the weird backticks on mod. We'll talk about that when we get to functions. All this is saying is, if x mod 2 is 0, if our x is even, then we want to return x. And the last example here, just showing what you can do with list comprehensions. If you just think about it for a second, if you want to know the length of a list, and let's say the list is from 1 to 10, what we can do is define a new list comprehension that takes every element from 1 to 10, and then we set a 1 for every element we have and add them all together. So we take every element from 1 to 10, put a 1 in that new list, and then sum them all together, and we get 10. So it's just how you can define length in terms of list comprehension. It's not how it's actually done, but it's just, an exercise for thinking about how to do it. So here's an example I want you guys to try. It'll be a little bit tricky, but it's a good example for learning list comprehensions. Credit note, I took this exactly from the Learn You a Haskell book, so it's not my example. But the question is, generate a list of right triangles that have integer side lengths less than or equal to 10, and have a perimeter of 24. So you can see that there's a couple parts here. The first one is you have integer side lengths. So we're going to be doing something like defining x is between some range of integers. The next thing we have here is less than or equal to 10, and have a perimeter of 24. And what we have over here is we have x mod 2 equals 0. That's like our filter. So we need a new filter for the perimeter equaling 24, and you'll have to put that right there. So get started on that. I'll give you a couple minutes, and you can ask me questions, and you can work with people around you too. So go for it. So here's the solution. The first line I just put just to show you can do it in one line of Haskell. So it's pretty tricky to do something like this, or it takes a couple lines in our language. But in Haskell, you'll see that lots of things you do that are really verbose turn into like one line. So here's like the line splitter version. The first thing you want to do is return a list of all these tuples. So all these pairs of 3 elements. So x, y, z is the names of our variables. The next part, we're defining our 3 variables, x, y, and z. Now you could have done from 1 to 10, 1 to 10, 1 to 10, and that would have worked, but you would have gotten a duplicate. So I did a little trick here, and I defined that x is always less than y is less than z, and z is from 1 to 10, because it's a right triangle. And so that avoids duplicates. But that's confusing, just use 1 to 10, 1 to 10, 1 to 10. And then I have these, I separated by comma the 2 filters I have. The 2 filters I have, just like the x mod 2 example, is the first one is saying if it's a right triangle. So z squared is equal to x squared plus y squared. And the last filter I have is x plus y plus z equals 24. The perimeter is 24. And so the answer you should have got is just 6, 8, and 10. And if you got to duplicate, that's fine. So you can see that in Haskell, even just in a simple list, you could do something like this. Okay, let's get on to functions, something more useful. So let's start talking about the type of a function. So again, you don't have to type the types. Let me just quickly show you. In GCI, I need the let because it's GCI. Then I can type div a/b equals a divided by b. And it lets me do that. I don't have to set a type. But I like to set types because it's clear what I'm doing. So the type of div is given by, and then you have these 2 colons, and then you have 3 floats here. So the first float says the first argument is a float. Second float says second argument is a float. And the third float says we're returning a float as well. And so this seems kind of weird at first because the return value is like grouped with the arguments and like there's no distinction. And we're not going to cover like in detail why, but it's something called currying. And the cool thing in Haskell is, so I define this this div function right here. Well, I don't have to give this div function all of its arguments, which is really cool. I can say like I can give div the like divisor argument, and I can make a new function that takes 1 argument. And so what this type thing is saying is it's saying that if you call div by itself with no arguments, it'll give you a function that takes 2 arguments and returns a value. If you call div with 1 argument, then it's going to be a function, they'll just look at the last part, it takes 1 float and it returns a float. And if you give it 2 arguments, it just returns a float, that's it. And so don't worry about it, it doesn't make sense, but it's like why, it's called currying, it's why it looks like that. So the more important thing is we define the type, and then we give the name of the function. We give the 2 arguments separated by spaces, and then we say equals, and after equals there's the function value. So note that there's no like braces or semicolons in Haskell. It's very clean. You're actually allowed to use braces and semicolons. This code by the compiler gets translated into braces and semicolons because it's easier to parse, but it's much nicer to write it like this. So div a b is equal to a divided by b. So it's a very straightforward function. Let me just take an aside and talk about infix functions real quick. So we define this function div ab, but it would be really annoying if we had to do like div for 2 instead of for div 2, which is more natural. Like there's some operators that are binary operators. You want 2 arguments, you want to surround them, you want to put the function in the center. And we can do that. Any function that you have, you can call it with the arguments like you normally would, or you could put it in the middle of your arguments and just put backticks around it. So before we saw the mod example, so here we have mod 3.2, and mod 3.2 gives you 1, but I really want to write it like this, 3 mod 2. And all I have to do is put backticks around it and I can do that. And you can do this with any function. The next example is really cool. So in most languages, things like addition and subtraction are defined like inside the language, but Haskell, like I was saying, it's very powerful. Everything's defined in terms of itself. Addition is just a function. So when you do 2 plus 2, you get 4 here, but I can also say plus 2, 2, and it can do the same value. The first one is using the infix form of plus. I can put any function in between the arguments and use it in the infix form. And if I don't want to do that, I can just put it in the front. In this case, I need the parentheses just for parsing, but it's the same thing. I can do div or mod in the front as well. And I can also define new functions that are just symbols. I can define a function that would be like that, for example, but I don't want to, so I'll do something like this instead. Something more straightforward. And I can define this to be my div. It takes 2 arguments, a and b, and it's equal to a divided by b. So now if I do 4 divided by 2 like that, it still works, because I'm using the infix form of the function. So that's actually very cool. Oh, and you can also get the type of functions. So we define div, right? So again, this is the most general type. You can see there's still like 2 arguments and 1 return value over there, but this is the most general type. And if I want the type of plus, I can do that too. So that's very cool. Alright, so now back to our division function. There's one flaw in this division function. It's somewhat obvious. There are some cases where it's not going to work. Who can tell me what the flaw is?
0.
B is 0, right. So we want to get into some kind of check. We want to check whether b is 0 or whether b is any other value. So how do we do that? One approach is to use the general imperative way with if statements and case statements. So Haskell has both of these things. In Haskell, you can use an if statement. So if, then condition, remember no parentheses here. You need the then, that's a little bit different. And then you just have the block of code for the case where that condition is true. So if b equals 0, then we're going to throw an exception. This error is similar to throwing exceptions in C++ in Java. So the exception is divide by 0. And if b is not equal to 0, we're going to go to the second case, so a divided by b. So that'll solve our problem. We can also use case statements. Case statements are a bit more common in Haskell. This is just saying, check b. If the case is 0, run the code after the arrow operator. And this next one is a little bit weird. So the underscore just means I don't care about the value. It's like the default argument of the case statement, or a switch statement, for example. In Java and C++, you have the default keyword. Here you just put an underscore. And the underscore is used in more places. So it's used in more places than this. It just means the default. The problem is this is kind of ugly actually. It looks really like imperative code, and so there are nicer ways to do these things. The first one is called guards. Guards essentially take the if statement. They kind of break the if statement into two functions itself. The first function body is defined by the first equal sign, and the second function body is defined by the second equal sign. So what we're saying is div takes A and B, and we put a pipe sign. And the pipe says, and by the way, this can be in the same line, I have to put in the second line for clarity. The pipe says that, check this condition. If B is equal to 0, then throw this exception. And then if that works, then that's it. It just stops right there. And if it doesn't work, it goes to the next condition by the pipe sign. And we say otherwise, do A divided by B. And otherwise is something just for readability. You could have done true, for example. Like, no matter what, do this. And in fact, if you look at otherwise in GCI, it's defined as true. It really equals true. So this is guards, and it's much nicer because each equals is like its own function body. So it's much nicer than if. But it is a better way to do this in Haskell. And it's called pattern matching. Pattern matching is a really nice feature that Haskell has, and now lots of other languages like Scala and Rust are trying to take from them because it's so nice. Here's an example. We have the same div function, but now our first function body says only run this code if the structure of the second argument looks like this. So if the second argument looks like a 0, then only run this first line of code. Otherwise, if it's just any old B, then run the second line of code. So what pattern matching is doing, it's literally just matching patterns, matching the structure of the data you're giving it. Right now it's really straightforward because we're giving it a float. If you give it a float or integer, you just put another integer there and define a case for that. If I wanted to do div A1, I could write 1 in the second spot and have a separate code path for 1. But we can do more complicated things than this. So here I defined a simple sum function. Let me just walk through the sum function first. The sum takes, the type of the sum is it takes a list of integers and then returns an int, so the sum of the list. The important part is the second line here. So if you want to define sum recursively, it's just the first element plus the sum of the rest. It's a very simple definition. So now let's get to the pattern matching. You can match any data structure by its pattern. So the pattern of the first one is an empty list. So I just put an empty bracket there. Now Haskell says if the list I get is empty, then I'm going to return 0. The second pattern is a little bit more confusing. If you remember the cons operator, what constructs a list from an element in a list, that's exactly the cons operator. So we're saying if the structure of the list we get is an element followed by a list, then call the first element we get x and call the rest of it x's. So x is just like a plural of x. It's a very common convention. But you can name it whatever you want. You can name it any variable. So we're going to say add the first element we get, x, plus the sum of whatever we get later on. So this is going to recurse. And then finally, sum of xs, this last element here is going to be x plus an empty list. And then xs is going to be an empty list. And then it's going to match the first pattern and stop. So recursion is just a base case and then like this step. And you can do it very cleanly with pattern matching. And note that we could also use the head and tail functions to extract the first element and the last element. But pattern matching lets it do it for you. Does it for you a lot more easily, and it's much cleaner. And just to drive the point home, we can match any structure. Like here, I've defined a list of size like that has one element. I'm calling it x. Here, I'm calling it the first element x and next one y. So the length of this list is 2, and I can just do that. So it's more verbose than that, but you can match any structure that the data structure could take on. And I have one more example that's actually very complicated. You don't even know the details behind this. But I just want to show you what pattern matching can really do. We've all written, if you're taking, I think 280, you've written some kind of tree structure, data structure before. And it's kind of a pain in the ass in imperative languages. But it's really straightforward in any recursive language, any function language. So the first line defines in a tree, what a tree is. Don't worry about the syntax. It's just saying a tree is either null, like an empty node, or it's a tree, the left tree, the middle value of the node, and then the right tree. So just a regular binary tree. And then what we're doing here, look at the contains function. The contains is looking at a tree as the first argument, and then an integer as the second argument, and returns a bool. So the first argument, Haskell is checking whether the structure of the tree is nil. And if it is, run the first code path. If the structure of the tree is a node followed by 3 values, run the second code path. So we're not saying, using one function and saying, if node is nil, do this. If node is this, do that. we can define it in this. If we want to have one more body statement that says, what if we want a case where both the child trees are null, both are nil? You can define a new pattern, node, nil, v, nil, and it'll automatically match that pattern and run that code path. So it's very powerful. It's a lot more straightforward than having a huge code body with if statements. Okay, so now you saw the sum function from the last slide. There's also one problem with this, and this one isn't an error thing, it's an efficiency thing. And if you've taken 280 and definitely 281, you should be able to quickly figure out what the efficiency problem with this code is. It's not tail recursive, right? So if you haven't taken 280, you can write recursive functions, but they'll be really slow because they take a lot of memory. But if you write them tail recursively, then they won't do that. So that's the gist of it. So we want to make this function tail recursive now. So how do we do that in Haskell? It's kind of messy. Just like in any language, it's really messy. So now we're going to have a helper function like we normally do, and then we pass to this helper function a new argument that's accumulating what the sum is so far. Then the first pattern check says if the list is empty, the result is what we have so far. The second pattern check, if the structure of the list is an element plus some other list, then we're going to add that element to our sum so far and then recurse on that. So it's very straightforward tail recursion. But tail recursion in any language is really nasty. Like our previous example, this is very clear. When you write Haskell functions, you often define the functions in terms of what the definition of it actually is. The definition of a sum is the first element plus the sum of the rest. It's the definition of it. And we can just literally write that. It's really nice. This does not look as nice. So the question is, do we always have to get rid of this in Haskell? When I started doing Haskell, this is really annoying to me, that I have to do this for efficiency. And the answer is no. There are functions we're not going to talk about in this talk, but later you'll definitely be using if you get into Haskell, called fold L and fold R. And they abstract this away from you. So in Haskell, there are a lot of different patterns you run into, because this is a very big language, and there are always functions and data structures that will do the exact same thing, but abstract away the details. So here's an example of how clean this same tail recursive example looks with fold L. And don't worry about what it's actually doing, but it's calculating the exact same thing. It's just doing it in the background for you. Okay, so this is another example we covered. Did you have a question?
Yeah, go back there. Could you actually replace that lambda with just the plus operator in parentheses, or is that not possible?
You could do that. Yes, you could do that. Yeah. So this is a lambda. So a lambda is an anonymous function. You probably, if you know C++ only, you're not going to know what that is, unless C++ 14 I think has it now. But essentially, it's defining a function without a name. And he's asking, can you use the plus function instead, which is already defined for you. And the answer is yes. Okay, so here's another example. Now you know pattern matching, guard statements, how to do errors. It's a little bit tricky because it's the first time you saw it. But write a function that finds the maximum element of a list. And if you're having trouble with Haskell, think about how you do it in a imperative language. You got with recursion. There's a base case, and then there's another step you need. And then write those out with guard statements and pattern matching. So I'll give you a couple minutes to do that. And again, you can work with people around you. You should write this in the file, by the way. And I mentioned before, if you want to load a file, then you do the :L, and then you load it. And if you want to reload it after that, just type :R. So it's better to do this in a file. And Haskell is a common convention if you're writing a function that's like another function, like if you want to write a new version of it, you write the name and then you put an apostrophe after it. It's kind of weird because you'll end up seeing functions that look like that. But if you want, you can just put an apostrophe after it too. You need to find the next function. So let's talk about the solution. So it's a little bit tricky because you have to use all three of the things we learned so far. The first thing you do is you pattern match on an empty list. If the list is empty, you throw an error, must provide an empty list. Second thing you do is you define your base case, where if you have one element, the max of the list is just that element. So now the thing is, you do something greater than your base case. What you do is you deconstruct your list into that first element and the rest of the list. Then you say if the first element is greater than the max of the rest of the list, then it's just the first element. That's the definition of the max of the list. Otherwise, just return the max of the list. Yeah?
Won't that always go recurse down to an error?
No, because we added this max of one element. Yeah, good question. Yeah. One thing you might notice though is that we're calling max this list twice here, and that's kind of weird because like you don't want to call a function twice, and it's going to be slower because of that. In Haskell, there's a way to define the result of maxes as you go along, but I don't want to keep throwing syntax at you; you're going to forget. So it's called a where clause or a let binding. Those are two ways to both define the maxes and store it for later use. But this isn't that bad. One reason is because, again, I said Haskell is lazy. It also uses something called memoization. And you learn about memoization in 281, where if you compute a value and you need to use it ever again, it'll keep that value for you. And I believe in this case, it'll keep the max SS value for you. So the second time you call it, it'll already know what it is. GCI and Haskell is smart enough to store these values in memory for you. All right, let's talk about laziness real quick. So I wanted to point out that in Haskell, like a lot of things you write are also very small. This is going off the end of the slide, so I apologize about that. But we can define quicksort in one single line, which is really cool if you've taken like 281 and you hated quicksort. If you don't take 281, that's not the point of this lecture. It's just that like if you filter the first half by the partition element, you add in the partition element, and you filter the left half or the right half by that. Add it all together, you have quicksort. So it's one line. So that's not the point of this, though. The point is, quicksort is n log n. Again, if you're taking 2 or 3 or 2 in 1, and that's not bad. But if we just want the first element of the list, the head of the list, it's really annoying to run an n log n operation and then just get one element from it. It's really annoying. So instead, what we do in Haskell is, if we run this code, it's going to be an O of n operation. And the reason is because Haskell is lazy. So head is the very first element. You don't need the second half of the list. So quicksort starts here with this filter function, which again I just said pulls out the lower elements from the partition element. And what it's going to do is it's going to sort the first half of the list. Head is in the first half of the list, which means that we don't need to do any more work at this point. Quicksort stops before it does the second half. Because we only need the first element. So I think that's really cool. We've taken this really slow operation, and we've reduced it down to almost only what we need, because Haskell is lazy. So that's a really nice feature. Sometimes laziness is actually tricky because it's hard to reason about these things, but often it'll optimize your code in these cases. Yeah.
So I gave a question in 281 homework where it was like this, except instead of head, it would be a kth element in the array.
That'd be all the kth element in the array. Yeah.
So would Haskell also optimize that and choose what side?
Yeah, the actual formula is going to be like n plus k log k or something like that. So it's going to keep being efficient until the very last element, something like that. All right, this is the last example. So essentially, it's like the same level as the last example. You just got to, given a list, just reverse it, return a reverse list. And the operators, if you might have forgotten what the operators are, you can use like this is a list of characters, so I can do that. And if I can also do something like that. So there are two ways to construct lists from smaller elements. So given a list of integers, reverse it. What was that? Yeah, and don't use the built-in reverse function to do it. Okay. So here's a solution. It's a little bit easier than the max example, but the tricky part is thinking about the recursion, like what's actually happening, what reverse is defined as. So it takes one argument, that's a list of integers, and it returns another list of integers that's just reversed. The base case is pattern matching on an empty list. The reverse of an empty list is an empty list. The second one says if we don't have an empty list, if we have an element plus an empty or some list, then reverse is defined as the reverse of the rest of the list, and then you add on the element you just picked off. So that's defining reverse. There's, again, like all these implementations, there's a single problem with this. It's also about efficiency. We can know what that problem is. It's a little bit more tricky. Yeah.
It's not co-recursive, but also appending requires you to reverse the list.
Exactly, yeah. So you should know this from, like, in most Java, C++ languages, if you do like string plus string plus string plus string, what they're actually doing is every time you have a plus, you make a whole new list in memory, and then you add the next part of the list. Then you make a whole new list for the next one, add the next one. That's exactly what this is doing. Every time you do reverse XS, and you concatenate an element to it, you're making a whole new list in memory. And then you got to do the same thing for the next iteration, and so on until you finish. And so this is very clean, but just like I mentioned before, with fold L and fold R, there are efficient ways of doing this computation. We don't have time to get into them, but Haskell, you can also do efficient things cleanly and efficiently. Okay, so that was all of my talk. I wanted to kind of mention, what else is there to see in Haskell? So we covered almost like the bare minimum in Haskell just to get started with simple programs. I mentioned querying and higher order functions. So Haskell is really nice about being able to pass functions around. In C++, you got to pass pointers, and it's really annoying. Haskell, like almost everything you do, involves passing around functions. We didn't even get to input and output, and the reason for that is I mentioned in the beginning this purity concept in Haskell, where if you call a function, it gives you the same value no matter what. That max function or the sum function, if you give it a list, it'll never change the value. Where in C++, it might be a member function of a class, and there might be an if statement and it changes depending on the variables in the class. So it can change. So that's not pure. But I/O itself, by definition, is not pure because we give it values, so the values it's going to give us back are going to change. So it's not hard to do I/O, it's just that the concept is a little bit tricky if you don't have enough time to cover purity. So that's another thing we didn't get to cover. Type classes, if you know Java, they're like interfaces, even though C++ are like abstract classes, but they're much more mathematically rigorous, and your code is much cleaner when you have them. And if you saw the, in GHCI, the T of like 1, for example, we're using a type class, and that's generalizing what the int actually is. And type classes are used all over the place. Monads, functors, and algebraic data types all go into the higher kind of types thing I was talking about before. And that again is what gives why Haskell is able to do all these cool things and all these cool features exist in Haskell, but not other languages like Lisp, for example. And the list really goes on and on. You can be learning Haskell for years, and you'll find a new style of writing Haskell that you've never seen before. And if you want to keep learning Haskell, so I highly recommend this first book at the top. It's a free book you can find online. It's called Learn You a Haskell for Great Good. I don't know where the title comes from, but it's a really good book. We covered pretty much like the first 2 or 3 chapters just in this talk, and the rest of it is getting to really interesting things in Haskell. The next link is a link to 99 problems in Haskell. Most functional languages you find will actually have a 99 problems page on the wiki, and they're just things like we covered, sum, reverse, but they're more complicated than that. And going through that will really, if you need some practice, go through that. And this last thing is a book that's also freely available online. It's written by Brian O'Sullivan, who's written a bit of the GC compiler, and a lot of the libraries you're going to be using as a Haskell developer. He works at Facebook, he's who I learned Haskell from, and his book is really good. So if you actually want a real book to read from, then you can use that. Alright, so with that, are there any questions on Haskell, or related to other languages, or, yeah? Yeah, it's on Dropbox. I'll post it right after this. Yep. And it's recorded, so you can get enough questions. Yeah.
Where are like the main uses of Haskell in the real world?
Yeah. So like you saw before, it's really nice to write Haskell code because when you define the code, it looks exactly like the definition of the function. So you can use Haskell for any case, like anytime I write a Python script, for example, you can use Haskell for it. You can use Haskell for systems programming if you want to do databases, distributed systems. It's very nice for that because everything is so clean by definition, what it actually is, and because everything is pure, you run into less bugs. 99% of the bugs you run into when doing our class projects are because of state. There's state in the program. The functions are not pure. In Haskell, your functions are always pure, so you're going to get rid of 99% of your bugs if you use Haskell. The only problem with using Haskell for these cases is the efficiency side, where laziness can help in terms of complexity, like O of n log n going down to O of n, but there are certain specific cases you got to watch out for where evaluating is actually do what you want. And Haskell fixes this problem. If you go look at the documentation, there are strict classes, and strict classes just get rid of all the laziness, and you can choose which one you want to do depending on that. So you can use it for whatever you want. You just got to be careful about it. It takes a while to learn Haskell actually to do it in its actual real world problems, which is why people haven't been doing it yet. But they're starting to. In Facebook, in London, there's actually a Haskell team there that's putting out code and stuff like that. Yeah. Any other questions? Yeah.
Are there any courses yet in Haskell?
Unfortunately, no. I really wish there were more programming theory courses here. Just for Haskell, for functional languages, and just for programming theory like static types, dynamic types, higher kind of types, things like that. We used to have one a few years ago when I was a freshman, but the professor left for some reason. And we've been trying ever since then to get a good professor, and we haven't been able to find one. So we don't have any, but I recommend looking online. Stanford, Berkeley, Carnegie Mellon are huge programming language schools, and they have a lot of material online that you can learn from. Yeah. Any other questions? Okay, well, thanks for coming. I'll be here if you have any more questions for me.